have bigger air cells due to air sucked through the pores of the egg over time. This is why rotten eggs float, because it has accumulated too much air inside its air cells. The eggshell is the hard protective cover of the egg, made up of calcium carbonate. Its color doesn't necessarily indicate the egg's quality or nutritional value. Eggshell color varies because of the various pigments deposited during egg formation. Usually, if the hen's earlobes or feathers are white, white eggs will be produced. If these are red, they will lay brown eggs. The shell membrane keeps the yolk and white of the egg together and protects it from bacteria. These are strong and made partially of keratin, a type of protein also found in human hair. The egg white, or the albumin, which cushions the yolk, is composed of 10% protein and 90% water. As food, egg whites are useful as binders for baking. And because these are high in collagen, a protein that promotes skin elasticity, egg whites are also used to make face masks. And finally, the egg's yellowish center, the yolk. It makes up 31% of the entire egg weight and contains plenty of vitamins and minerals. The color of the yolk is dependent on the hen's diet. Eggs from pasture-raised hens are said to have more omega-3 and less cholesterol due to its consumption of natural feed.
The South African Constitution is regarded by people all over the world as one of the best examples of a modern constitution. It makes clear what kind of country we want to be, which is an open, just, and democratic society based on dignity, equality, and freedom. And the rights in the Constitution help realize these values. Rights like access to housing, access to education, and freedom of expression, which are all intended to improve our quality of life and free our potential. So our Constitution is good, and it does a lot of good, but there may be times when it needs to be changed.
So that it keeps abreast of developments, because it is supposed to be reflecting society at any given stage.
Between 1996 and 2014, it has changed 17 times. To make any changes, here's what always has to happen. First, the change needs to be proposed in Parliament. Because the Constitution is meant to be the voice of the people, the state needs to arrange public hearings to ask South Africans what they think of the proposed change. These public hearings might impact whether or how the amendment should be made. Thereafter, Parliament votes on the amendment. Most parts of the Constitution require 66% of votes to be passed, but amendments which change the core values of the country require 75% of votes to be passed. The Constitution is difficult to change on purpose because it details the core values on which our country is built, so any changes should clarify or improve how it works for our democratic society, promoting dignity, equality, and freedom.
Welcome to another beautiful Tuesday afternoon. Welcome so much to the show. My name is Tobile, and I want to send tons and tons of love to Liberty. Thank you so much once again, guys, for sponsoring the show. Thank you so much for giving us the opportunity and this platform to actually help the class of 2021. Another thing, grade 12s, if you haven't done it by now, please do it as soon as possible. Do download the Tenfold education app. It is an app filled with tons and tons of past papers that can help you guys prepare. I know you guys are currently busy with the prelims, and you can use and take any help that you guys can get. Another platform where we are active is on WhatsApp, and this is the questions we're doing today. If you want to join in, please do send a hi to the WhatsApp number on the screen, and we shall send you the questions. Also, if you want more help, please do find us on YouTube, and on YouTube, there you can follow us on Mindset Learn. So in today's show, we are doing all about the photoelectric effect and, light phenomena and all that stuff. So this is not a difficult question. It's just a little bit tricky. But I feel like if you can get hold of the terminology that is used, and I'm going to find like normal examples on everyday things to actually help you guys understand this topic. You cannot fail this one. It's very simple, and the questions don't really change that much. So with this one, we have the question, and it says the threshold frequency. Already, when you see the word threshold, it means something. We do have a normal frequency, and then we have a threshold frequency, where the minute you see threshold, it is the minimum frequency that is then required to actually emit or eject an electron. So the threshold frequency of two metals, which we have is cesium and potassium metals, are given in the table below. So here's our metals, and here's the threshold. So I can already see that, okay, everything is in hertz, so that is correct. Now I can see that the threshold frequencies are not the same. This is because, remember, different types of materials, or metals in this case, will have different thresholds. Like metals don't really have the same, are not really made of the same substances, and don't have different surfaces. Some are stronger than others. So this means different frequencies will be required to eject those electrons, like a plane ticket. If you're going to the USA, you're going to need a different amount for your plane ticket than if you're going to a country in South Africa or near South Africa, right? It's quite very different. So it's the same thing with metals. Every metal has its own threshold frequency. These are the two that we are given. So the first question says we must define the term work function. Now, like I always preach, grade 12s, you cannot fail because you are lazy to read. So the definition for threshold frequency, usually in grade 12 definitions, are only for 2 marks. So work function of a metal is the minimum energy which is needed to eject, you can also say emit, eject an electron from a metal surface. So whoever will be marking your paper, one important word that they're looking for is minimum energy. If that word is omitted, you might actually forfeit all your marks. But the definition for work function is the work function of a metal is the minimum energy needed to eject an electron from a metal surface. So remember, with the photoelectric effect, metal will have a work function. When the light is coming on that metal, it will have its own threshold frequency, or the metal also requires its own threshold frequency. So we've already learned about 2 things. So that's the definition for the 1. So for 1.2, we are asked which one of the 2 metals in the table has a higher work function, and give a reason for your answer by referring to the information on the table. So I'm going to do it the long way around so that everyone knows exactly what's going on. So as you can see, this one is 5,07 times 10 to the exponent 14 hertz. This one is 5,5 times 10 to the 14 hertz. Now I can already see that this is 5.5. This is what I always tell my kids. Most of the time with the threshold frequency, if they're asking you which one is greater, which one is lower, and so forth, think about money. If you had 5 rand and 7 cents and your friend had 5 rand and 55 cents, your friend has got more money than you, right? So now, remember, this is physics. We need to actually kind of sort of prove what is happening. So I can already see that potassium has got a greater threshold frequency than cesium, because that's 5,55. where the other one is 5,07, so I can already see it is. But this one says threshold frequency. The question says work function. So that means I need to find the relationship between work function and threshold frequency. I'm going to do it the long way around. So remember, we have a formula that says E is equal to HF. Then I can say E is equal to H and threshold frequency. Then I can therefore say work function is equal to HFO. And you know, this is an equal sign. This is not a fraction on this side. So the work function is directly proportional. The work function is directly proportional to the threshold frequency, which means that when the threshold frequency is high for potassium, it also means that the work function for potassium will be high, which also means that if the threshold frequency for cesium is low, the work function for cesium will also be low. That's what directly proportional means. But now we have to give a reason for our answer. Now, remember, when you ever have to give a reason for your answer, don't give something out of the blue to say, look on the table, because potassium has this and this. Remember, I always teach my kids, go to the formula and use your formula to actually elaborate or explain your answer. So I'm going to show you two ways in which you could have actually done. So the first one, we could have just said it's directly proportional. So I could have just said the work function. I must first state which metal. So potassium first. So potassium has a higher work function. Potassium has a much higher work function. I'm going to use a dot so that you are with me. So the first one I could have said work function. I see it from my formula, yeah? Work function of a metal. Metal is directly proportional proportional to the threshold frequency. Threshold frequency, where work function is the minimum energy required to eject or emit an electron, threshold frequency being the minimum frequency to eject an electron. Or you could have said, so the blue is just another option, which means you could have said potassium has a higher work function, and they do say give a reason for your answer. Remember, it must be a reason that makes sense. The first one I got from my formula of work function is equal to H and threshold frequency. My second reason I could have said that the threshold frequency for potassium, and the examiner will agree with you because this is what you are getting from the table, is greater than the threshold frequency for cesium. For cesium. So now you're already going back to the table and showing the examiner potassium has a greater threshold frequency than cesium. Now let's elaborate. What does that mean? Therefore, the work function will be higher. I think this question was also just for 2 marks. So you've already shown the examiner that you have seen a relationship. Remember, guys, you do get a point or a mark for saying or identifying which is the equation. Don't just get into explaining your answer. They do ask which one of the 2 metals. So the examiner wants to see if you've chosen potassium or you've chosen cesium, right? And then they also want to see the reason that you've given. So you're going to get a mark for writing or identifying the metal, and as well as a mark for having the correct relationship. What I always tell my kids, if you have to give an explanation or giving a reason, always go to your formula. I promise you, if you can use your formulas to identify your definitions as well as giving a reason, because it's always directly proportional, inversely proportional, and so forth, you are most likely to get this 100%. Let's go to the next question. So the next question is a bit of some information. So we have, they say the simplified diagrams below show 2 circuits. And this is circuit number A and circuit number B. They contain photocells. The photocells in circuit A contain cesium metal. This is the one over here. And remember, we already told that cesium has its own threshold frequency, while the photocells in number B contain potassium. We've also learned that potassium will have its own threshold frequency. So already just by mere looking between A and B with what we are given, we already identified that potassium has a higher threshold frequency and potassium will have a higher work function. So already that light bulb must be going through your mind. So let's see what the question's asking. So the question says ultraviolet light. So this is the type of light that they're going to use. So now remember, this is when we learned about ultraviolet light and gamma rays and infrared and all that stuff. That was grade 10. So now there's different types of light. They have different types of frequencies and different types of wavelengths. So now they've chosen ultraviolet light. So this means for both of them, we're going to use ultraviolet light. But remember, both of them, or cesium and potassium, have got different threshold frequencies and different work functions, which means we're not going to get the same results. Already keep that lingering in your mind. So ultraviolet light with the same intensity, which means the intensity for potassium as well as the intensity for cesium is exactly the same. It's important that they say same intensity because if the intensity was to change, it could actually change a number of things here. So with the same intensity and wavelength, so both for A and B, meaning cesium and potassium, they use the same intensity as well as the same wavelength. So this means this was our controlled variable in this experiment. And my wavelength, this will just be a -7. Wavelength of 5,5 times 10 to the -7 meters is incidented on the metal plate in each of the photocells, and the ammeter in circuit A registers current. Remember, ammeter is what we measure current with photoelectric effect. If we are able to emit a generous amount of electrons, and the flow of electrons means we are generating current, just like electricity. If we are able to have current, we can actually find the resistance and the potential difference and so forth. But that's what the photoelectric effect is all about. We are trying to generate as much electrons to flow through so we can actually get amount of current. So now let's see what the question continues to say. It says, by means of a calculation, determine whether the ammeter B will register a current. Now, remember what we were told. We were told that this is the light that will be shown on B. B is potassium. We do have the threshold frequency for B. So will B have a current? So now I want you to think about this logically, then I'm going to make an example for you. If B has got a threshold frequency of, I think it's 5,07, let me just double check, which is potassium. It's 5,55. So potassium is 5,55. Now, that's what it needs to actually eject. That's the frequency needed to eject that electron. And then we've got UV light that's coming with an intensity and a wavelength, but the frequency that it's going to come with does not really, it doesn't match the standard of this one. Will we actually eject an electron? It won't really work. Take it like this. You want to marry a bride, and the father says, I want a minimum of 1,500 Rand, and you only have 1,000 Rand in your pocket. He wants a minimum of 1,000 Rand. You can go higher if you please, but if you don't have 1,500, you don't leave with your bride. You only have 1,000 Rand. So this is what we need to check. If we can prove that the frequency of the UV light is greater than the threshold frequency of potassium, then we can have a current. But if the frequency of the UV light is less than that of the potassium, then we're not going to generate a current. So that's what we need to prove. We need to find the two frequencies and see whether it is greater than, equal to, or smaller than. So let's start. I'm going to start with what I am given. So there's two ways in which I found that you can actually get this answer. So let's do it one step at a time. I'm first going to find the frequency of the UV light because I already know the frequency of potassium. So this is an equation we learned in grade 10, which is C is equal to F and then lambda. Remember, it is a small c. It is a constant, which you get on your formula sheet. I'm just going to make F the subject of the formula, divide both sides by lambda. I'm going to end up with F is equal to C over lambda. Now I'm just going to plug in. C is a constant, which is 3 times 10 to the exponent 8 over. I am given my lambda. It's the one I'm given here. Remember, lambda is wavelength, and the wavelength is already in the correct SI unit. If it wasn't, you had to convert it. So that is 5.5 times 10 to the negative 7. I like putting everything in brackets so that your calculator does not do exponents first. 5,5 times 10 to the exponent negative 7. So let's see. So I'm going to put everything exactly as it is on the calculator. 3 times 10 to the exponent 8. And then I've got 5.5 times 10 to the exponent negative 7. Just double check that one. Yes. So I get 5,45. Remember, if the third number is less than 5, it doesn't change the number in front of it. So here I get the frequency of 5,45 times 10 to the 14 hertz. So let's see. Let's go up to potassium. Let's see what the threshold frequency, what does potassium need so that it's actually ejected? If I look at this one here, potassium needs a minimum of 5,55. This UV light that is being used in this experiment can only deliver 5,45. So no, he's not leaving with his bride. So this means that the frequency of the UV light is definitely smaller than the threshold frequency. Remember, the minimum frequency needed to eject the electron. It's smaller than that of potassium. And remember, the question did ask that, will we register a current? So I've just found the frequency, but I didn't say whether a current will be released or not. I've proved something, so remember to always give a statement. Therefore, remember they did say, will the ammeter have a reading? Therefore, the ammeter, remember ammeter is what we use to measure current. It is a device. The ammeter in circuit B will not show, ooh, almost wrote so, will not show a reading. So I've proved that, so already the examiner can see, okay, this child really knew what was going on, because they use the frequency that can be delivered by the UV light and the frequency required by potassium, and you can see that it's really not the same thing. Another way that you could have done, you could have used the work function. Now we know that from threshold frequency, we can find the work function that is required by potassium. Also, then we can say, okay, if the UV light is producing so much frequency, we can actually find the work function of that and then see how these two work functions compare. So I'm just going to say or here. So you could have done it in this way either. So you could have calculated that with this UV light that I'm given here, using the wavelength of it, I could then have found how much energy. Remember, energy is what we found from our first definition, which was my work function, meaning that my work function is the minimum energy. So if I can find what is the minimum energy that this UV light can actually give or produce in potassium, then I can then look at the two comparisons. So I'm going to do it one step at a time. I can therefore say, let me do it the long way around. So remember we have a formula, E is equal to HF. And F, we can also say, is equal to C over lambda. So where there's an F, I'm just going to substitute it by C over lambda. Stays E, H, C over lambda. So that's where I get this formula. If you do want to do it step by step on the side, you're more than welcome. I just like putting everything all in once. So let's calculate the energy. Remember, H is a constant, which is 6.63. multiplied by 10 to the negative 34. C is a constant, which you also find on your formula sheet, which is 3 times 10 to the exponent 8. Now, they told us that the UV light has got a wavelength of 5,5 times 10 to the exponent negative 7. So let's see that one. I'm just going to plug in everything exactly as it is. Remember, always put brackets around your stuff. It just works better. To the exponent negative 34, I'm going to have 3 times 10 to the exponent 8. This is a constant, so it's something you don't have to memorize. 5.5 multiplied by 10 to the exponent negative 7. Let's see what I get there. So I'm going to round it off to 2 decimal places. So this will be 3,62 times 10 to the exponent 19. So this is 3,62 times 10 to the exponent negative 19. Remember, energy is measured in joules. So that's the energy that the UV light will give. Now let's see what will then the work function of potassium then be. So I'm going to work here so that I can write my statement here. So I'm going to use work function. I've shown you how I got this formula before. I derive it from here. Threshold frequency is equal to work function. That's how I get work function is equal to HFO. Just write my H on this side. So let's calculate the minimum energy required for potassium. So we already know what the energy of the UV light can give, but how much energy or the work function that potassium actually requires. H is a constant, which is 6.63 multiplied by 10 to the exponent negative 4. The frequency, the threshold frequency of potassium was given on the table, which was 5,555 times 10 to the 14 it was, positive 14. Now let's find the minimum energy required. Put just your sums in brackets, 6.63 times 10 to the exponent negative 34. And we've got 5,55 times 10 to the exponent 14. And there I have it. So I get 3,68 to 2 decimal places times 10 to the exponent negative 19. So I get 3,68 multiplied by 10 to the exponent negative 19. And remember, work function is in joules because it's the minimum energy that is required. So now let's see the comparison. With the energy of the wavelength, I've got 3,62. The minimum energy required by potassium is 3,68. So this is again less than that one, most definitely. Remember, I first make a statement. I'm showing the examiner that I can see the relationship, or there isn't a relationship between the two, and then you make your statement. Why do we make a statement? Because they did say, will we register a reading? Will we register a current on the ammeter? So I want to show the examiner, no, there's no relationship here. So this means that I can therefore say that the work function is greater than the energy. The minimum energy is greater than that. So it means that it won't eject it. My statement can be, therefore, the ammeter will not register current. It will not register a current. And there we are. So you could have done it in 2 different ways. The minute you've got the threshold frequency, you can find the work function. So my first one, I decided to find the frequency that the UV light can give and the threshold frequency that potassium has, and then saw the relationship between the two. And I found that what potassium actually needs that the UV light cannot deliver. And I did the same thing with the work function as well as the energy. I found the energy that the UV light actually has as it's emitting the electrons, and then the minimum energy that potassium has as a metal. Then I saw, nothing's going to happen here. Then there's a comparison between the two. Always show the examiner the statement that you can see the relationship, or if there isn't even a relationship between the two, and then you give a statement. Just want to elaborate on this because I see some of you guys are still making a mistake with this one. Guys, this, if you're still struggling, this is small. Make a funny looking sign there, and this is big, right? And this one is definitely easy. You just write that, and this is equal. But I see a lot of you guys that are still very confused with the smaller than, bigger than sign. When you write it here, then it looks in all other different angles. So I always teach my kids like this, and the crocodile always eats the biggest number. So let's go to the next one. So this one says I must calculate the maximum kinetic energy. Now I know, okay, there is a formula where I can calculate the maximum kinetic energy of an ejected electron in circuit number A. Remember, circuit A was then that of cesium. I'm just going to go back here. So circuit A is cesium. However, they did use ultraviolet light with the same intensity as they did for potassium, as well as the same wavelength. Now we need to find out the maximum kinetic energy for circuit number A. So let's see how we're going to do that one. So remember, we do have a formula. I can say E is equal to WO. Now, I think you know by where I get that by now, but we do have a formula where we can say EK. Now, remember in grade 10, that's where we introduced kinetic energy and potential energy and so forth. So EK is kinetic energy. I'm going to break up the energy. Why am I going to break up the energy? Because remember, as a UV light is moving, it's got its own wavelength and its own energy. So we want to see the maximum kinetic energy that it will have from the same intensity as well as the same wavelength. So I'm going to break up this one, which is the E. So I can break up the E by saying it is hc over lambda. I showed you how I broke this up. Is then equal to, I can break up my work function to h and to my threshold frequency plus EK. I am breaking all of this up because work function is equal to h and threshold frequency. I don't have the work functions. I've just calculated the one, but that was for B. I'm looking for A in this case. So I know that I have the threshold frequency, the minimum frequency, which is then what I can substitute in here to find my work function. So let's plug in. Let me do it the short way around. I'm going to take EK to this side, this to that side. Remember to divide everything by 1. And then I'm going to end up with EK is equal to hc over lambda minus HFO. So I just literally swapped it around. Remember, if something jumps the equation sign, then the sign will change. So H is a constant, which is 6.63. multiplied by 10 to the exponent negative 34. C is the speed of light, which you don't have to remember, which is 3 times 10 to the exponent 8, all over the wavelength of the UV light, which I was given as 5,57. 5,5, let me just double check here quickly. 5,5, just 5, not 5,5. 5,5 times 10 to the exponent negative 7 minus H is a constant, which is 6.63 multiplied by 10 to the exponent negative 34. My minimum threshold frequency, they did say for A, and A is cesium. I'm just going to go back to my table up here. It is cesium. That was the one that they had. The threshold frequency was 5,07. Let's check it out here. I can see that for circuit A, which is in question, we do have cesium there, which means I can use a threshold frequency for the cesium metal. So I'm just going to plug it in there. So this is 5,07 multiplied by 10, and this was given times 10 to the 14. So I'm going to plug this in a calculator exactly as it is. I just want to say something quickly, guys. I know I always do everything and plug everything in the calculator all at once with brackets and so forth. If you do want to do your method step by step, you're more than welcome to. What I would advise you to do is, so that you can get the correct answer, is don't round off your answer, only round off your final answer, which means you might have a number with 3 values after the decimal, after the comma. Write it exactly as it is, because the more you keep rounding off your answer, the more incorrect it actually becomes. Though when you are actually marking and we have a memo, we do have a range where we mark, but you never know what range they are actually going to give you, or if there is even a range, because in some questions we don't get a range. We only have one specific question. So my advice to you, if you are going to break it up and not do it all at once like myself, write out the entire number and remember to put brackets in over everything. Okay, so let's see. Start with this one. So I've got 6.63 times 10 to the exponent negative 34. And I've got the constant of 3 times 10 to the exponent 8. And underneath that, I've got 5,5 times 10 to the exponent negative 7. Close that bracket. Minus 6.63 times 10 to the exponent negative 34. And right next to that is the threshold frequency for cesium, which was 5,07 multiplied by 10 to the exponent 14. And let's see what we get there. Let me just close my bracket there at the bottom. And therefore, I get 2,55. Remember, the third number is a 9, so the 4 will change to a 5, times 10 to the exponent negative 20. So the kinetic energy that I have is 2,55 times 10 to the exponent negative 20. Remember, the SI unit for kinetic energy is in joules because it is a form of energy. So that is one way that you could have done it. Or another way that you could have done it is we did calculate the work function over here. We did calculate that the frequency of the UV light was 5,55. So this is another one that I could have used. So this is, you could have used this one or you couldn't have. So it depends on how you're thinking when you're writing the paper. You could have already said, but I did calculate the frequency that the UV light will have. Why don't I just calculate the energy using this one? Or you could have thought, okay, this is what I have. Yeah, this is what I'm looking for. This is what I have. Can I not just calculate using the wavelength of the UV light and then using the threshold frequency of cesium? So you could have done it like that. Or you could have used what we had in the previous one. Remember, energy is equal to my work function. And remember, that's the one I have, plus my EK, which is therefore then my energy. Then here, instead of breaking it up with the wavelength that I'm given for the UV light, I can just substitute the frequency, and this frequency is the frequency that I got here, which is the 5,45, because I already calculated it in the previous one. And trust me, the examiner will give you full marks if you did it like this, because you're showing continuous assessment. Even though that frequency was wrong, plugging it in the right place will still give you full marks. So we've got 6.63. Let me just not skip steps. Let me just show you how I got to that. I'm going to break up the E into HF, not HFO, right? Or C is equal to lambda, just HF. And then I'm going to have my HFO right there, plus then my EK. Remember, this is 6.63 times 10. Let me just do this so that I can put everything in one line. I'm going to write here. So this is 6,63 multiplied by 10 to the negative 34. The frequency of the UV light that I calculated in the previous question was 5,45 multiplied by 10 to the 14 equal to, remember, H is a constant, which is 6.63 multiplied by 10 to the exponent negative 34. And then the minimum frequency for cesium was 5,07 times 10 to the 14. And then here, I'm just going to have EK. So you do exactly the same thing. So I just want us to move quickly. I'm just going to take these ones to the other side and subtract the 2. And then you should therefore then get EK exactly the same as how I wrote here in the yellow color, which will be 2,52 times 10 to the negative 20. Don't forget your SI unit for kinetic energy, which is in joules. So those are two ways that you could have done it. You could have thought, okay, let me use everything that is original, just in case you thought all the other ones were wrong. Then you say, I do have the wavelength for the UV light, so I could therefore use that, and then you can find the kinetic energy. Or you can say, but I already calculated the frequency, so I can just might as well plug in and have less things to calculate. If you use either or method, you will still get full marks for either or, because you're showing the examiner, you're using what you're getting, and then you just got your kinetic energy. And that is a mark in the box. Let's look at another one. So this one says, how will the maximum kinetic energy of the ejected electron calculated in 1.4 change when the intensity of the incident light, remember, when we intensify the incident light increases, we must say, will it change, will it remain the same, or will it decrease? So remember, only when we change intensity, nothing happens, so this remains the same. This remains the same. Only if the frequency of light is increased, then something can happen. But only if intensity happens, nothing. That means we're just going to have more electrons that are actually just being ejected. But only if the intensity of the frequency, therefore, can eject the ejected electrons will have greater kinetic energy. But if you just increase the intensity, we just have more photoelectrons that are being emitted, because then it's not only one wavelength ejecting and only one, we have a few moving all in all opposite directions. So in this one, we just had to say it remains the same. Let me just write an E. They didn't say you must write a reason, but if they did say a reason, intensity just means there's more ejected photoelectrons, but does not actually affect the kinetic energy in any point. And this is the first question that we've done. A lot actually to go through, but take a breather and I will see you after the ad break.
Did you know that the world's longest railway tunnel runs under the Alps? Inaugurated on the 1st of June 2016, the Gotthard Base Tunnel is the longest and deepest railway tunnel in the world. The tunnel is an incredible 57 kilometers long, reaches a maximum depth of about 2,300 meters under the Alps, and cost in excess of $12 billion to construct.
No one ever asks why we do the weird things we do. Like, why once is never enough? Or doing 2 trips is just one too many. Why do we, before we use these, or say 5, when we mean 20? Why do we have second thoughts? And think that lift buttons make them go faster? Why don't we walk there? Cross our fingers, touch wood, and struggle to hide our true feelings? At Liberty, we want to know all the weird and wonderful things that make us human, because human beings, being human, are what we make financial solutions for. Liberty, in it with you.
Welcome back. You're still tuned in at Tenfold Live, and I am Tobile. I want to send tons and tons of love to Liberty once again. Thank you so much for the platform that you've given us, and thank you so much for assisting us so we can assist the class of 2021 with their final exam question papers. I know they're busy with prelims right now, so all the best for that. And grade 12s, if you haven't done it yet, please do download the Tenfold Education app. It's an app filled with tons and tons of past papers that can help you prepare for your final exam papers. The time to download it is now. Your prelims are currently on the go, and you need as much help as you can. If you're wondering what question papers we are doing today and you'd like to join in the fun, please do send a hi on the WhatsApp number on the screen, and we shall therefore send you the question papers we are doing. Another platform where we are active, live, and awake is on YouTube. On YouTube, please do follow us at Mindset Learn. So right before the ad break, we're all doing about photoelectric effect. It sounds so fancy, but it's actually a very simple topic, grade 12s, and my advice to you, get 4 marks for this one. It's really easy marks. It's repetition of the same thing over and over again. You just need to understand the terminologies, and once you have that, 8 to go, and then you should be ready. So let's do another question paper. So this one is from Magandotana, and this is 2.1. So the statement says, in an excited atom. So I just want to explain what excited means. So we know that when we're doing the photoelectric effect, we have a frequency of light that wants to emit an electron. And sometimes it can emit the electrons and then they just shine or they just move a little. Or sometimes the frequency can come and then it gives the electrons enough kinetic energy to jump around and move and so that we can have current and all these things. So it has enough energy. Think about this. If you are thinking the tooth fairy is going to give you 1 rand for your tooth and then the tooth fairy gives you 10,000 rand, you're going to be extremely excited. So the electrons are something like that. When the threshold frequency gives the electron enough kinetic energy, it makes it excited. But this all happens in different energy levels. So In an excited atom, electrons can jump from lower energy levels to higher energy levels. Now, something completely different happens when it jumps from a lower energy level or a higher energy level, and vice versa. So what this means, we have what we call emission and absorption. Energy is either being gained or energy is either being lost. They can also drop from a high energy level to a lower energy level, right? So with emission and absorption, it's something else that they also bring in at the end of the Doppler effect, where you have the blue shift and the red shift and all that stuff. So this is just something more or less or similar that they're also bringing into this one. It's all about wavelengths and frequencies and different types of light and all that stuff. So now we're already told that they are moving, they jump from lower to a higher or higher to a lower, and they have words. It's either emission or absorption. So now we have the diagram below, not drawn to scale, shows some of the transitions from electrons in an excited state. So now let's see. I've got energy level number 2, energy level 3, and energy level 4. I can see that it's increasing going up. So which means from energy level number 2 all the way to 4, it gets higher and higher and higher and higher. Let me just write this. This is 2, this is 3, and this is 4. Let me just also write the E's. E meaning energy level, right? So if you're kind of getting confused, like tops, but I don't really understand it, there's arrows moving down, just think of it. Energy level 2, well, 3 will be greater than 2, and 4 will be greater than 3. But let's see. I'm just going to make a dot there. This one moves from 3 to 2. So let's read what we have. We move from 1,93. Let me just write out these numbers as well. So I move from 1,937 times 10 to the exponent negative 18 joules. And I move all the way to 1,635. I can see that I've lost some energy. Think of it as money, 1 Rand 93 cents and 1 Rand 63 cents. Definitely 63 is less. If I put a dot here, I move from energy level 4 all the way to energy level 2. At 4, I would have had 2,044, think about 2 Rand, times 10 to the exponent negative 18 joules. I can see all the way from energy level 4, a jump to energy level number 2, there was a complete drop, which also proves that energy level 4 is much higher than 3, much higher than 2, which means that 3 will be higher than 2, so 2 will be the least. And that is why it's increasing going up. So we've already looked at our graph. Let's see what they're asking us here. So now, do the transitions indicated in the diagram lead to absorption or emission? Remember what I said. If an excited atom moves from a high energy level to a low energy level, there's a name for it. Or if it moves from a low energy level to a high excited state of an energy level, there's also a name for it. So in this one, does it lead to absorption or emission? We can see that it moves from high energy levels 4 to 2 and 3 to 2. So it moves from a high energy level to a low energy level. So this means it is the emission spectrum. It is emission. It is the emission spectra. Now, I see here they didn't say give a reason for your answer. If they did say give a reason for your answer, the emission spectrum is when electrons move from a high energy level to a low energy level. Let me just write it down just in case. Emission spectra, when electrons move from a high energy level to a low energy level. To a low energy level. So that if they did ask for a reason, that's what we could have said. So let's look at the next one. Here we are asked to calculate the frequency of the photon produced when an electron in an excited state, remember it was on 4, excited atom makes a transition from 4 is to 2 as shown in the diagram. And then they want the frequency. Now remember, with the energy levels, it is then the energy already. And we know that we can break up energy into H and F, and they want us to find the frequency. But now we've got 4 to 2. So let's go back to our diagram. I just want to show you how we're going to do this. I see that it moves from 4 to 2. So this is what we're going to do. We are going to say energy level 4 minus energy level 2. Just like in physics, you know, most of the time we say V final minus V initial, and we find the difference between the two, and that is what we use. We're going to do exactly the same thing here. We move from 4 all the way to 2, so we're going to say energy level 4 minus energy level 2. Don't do it just on your calculator. Write it down and show the examiner how you got that. You will get a mark for that. So let's see. It's nice in physics to always start with a formula. So I'm going to say energy level 4 minus energy level 2. I'm showing the examiner that I'm looking for the energy. I want the frequency between this transition. So with energy level number 4, I had 2,044 times 10 to the negative 18. Put everything in brackets, minus. The first energy level, I had 1,6 multiplied 1,635, sorry, 1,635 multiplied by 10 to the exponent negative 18. So let's find the energy there. Plug everything exactly as it is in your calculator. 0.44 times 10 to the exponent negative 18. And then on this side, I've got 1,635 times 10 to the exponent negative 18. And therefore, that is what I get. 4,09 times 10 to the exponent negative 19. 4,09 times 10 to the negative 19. Remember, energy, my darlings, is measured in joules. You don't want to get penalized for that one. So now we've already found the energy, but the question said we must find the frequency of the proton produced. So now we're not finished. So now I'm just going to work here. Let me work. I'm going to take it there. Remember, the formula for energy is E is equal to HF. I just found my energy, but the question wanted frequency, so F is unknown. So I'm just going to plug in my energy is 4,09 times 10 to the negative 19. That's what I got from calculating it here. The transition between energy level 4 and energy level 2. H is a constant, it's Planck's constant, which is 6,63 multiplied by 10 to the exponent negative 34. F is unknown. I'm going to make F the subject of the formula. I'm going to do so by dividing both sides. Let me just do it the long way around, my darling, so that everyone knows what I'm doing. 6,63 times 10 to the negative 34. What you do on this side, you do on the one side. 63 times 10 to the negative 34. This and this will cancel, leaving F by itself. Let's put this in the calculator and see what we get here. Oopsie daisy. So I've got 4.09 times 10 to an exponent negative 19. All over 6.63 is a constant. You don't have to remember it. It is on your formula sheet. Negative 34. And let's see what we have here. This gives me 6,17. Because the third number is an 8, it will change the 6 to its next value, which is 7. Times 10 to the exponent 14. So that's my frequency. So this will be 6,17 times 10 to the exponent 14. The SI unit for frequency is capital H, which we call hertz. So that is then the frequency that I had. So the only thing that was a bit tricky here, you needed to first find the transition of the electron from the excited state of energy level 4 all the way to energy level number 2. So we did that by actually subtracting the 2. Then that was the energy that the electron, the transition. And then we had to find the frequency that would have been produced. So most of the time, as you will see in the previous question that we did, we had to calculate the work function, the threshold frequency. This was a bit of a different one where you actually had to find the frequency because you were given the energy. So it would have been wrong if you used the energy of energy level 4 or 2. You had to subtract the 2. Okay, let's continue. So I'm told that the threshold frequency of a metal, we're not told what metal this is, but we know from experience that different metals have got a different work function, the minimum energy required to eject or remove an electron from a metal surface. So we don't know what metal this is. So threshold frequency of a metal, which is Q, and they told us it's 4,4 times 10 to the exponent 14 hertz. So that's the threshold frequency, right? And then the question continues to say that we need to calculate the kinetic energy. So that is EK once again, the kinetic energy of the most energetic electron ejected when the photon produced in question 212 is incident on the surface of the metal. So this is the previous one that we have. We did find the frequency of 6,17 times 10 to the exponent 14. But now they want us to find the most excited. Remember what I said. If the wavelength emits the electron says, ta-da, I've got enough kinetic energy, it can therefore move around. So that's what the question is asking us. They want us to calculate the kinetic energy of the most excited electron that will be emitted. So let's see how we're going to do that. So formula first, and that's what will guide us with what we have and what we don't have. And this is all for metal Q. Remember, metal Q is unknown. My formula is E is equal to my work function plus my EK. You don't have to know this off by heart. They do give it to you in the formula sheets. Remember, I do have my E. That's the energy I calculated before. But I do know that I don't really have my work function, but I do have my threshold frequency. So I'm going to say HFO plus my EK. Just want to go up here quickly. So this is the energy that I have. This is my frequency. Let's see what else, other information I'm given. And this is the energy levels that I have. So let's see how I'm going to calculate this one. So with the E is what I already have from my previous equation, which is the 4,09 times 10 to the negative 19. Remember, H is a constant, so you don't have to know that. That is 6.63 multiplied by 10 to the exponent negative 34. Now, the threshold frequency that I have is 4,4 times 10 to the exponent 14. And then my kinetic energy is what I'm looking for. Now, the rest of this is then just mathematics. So I can take all of this to this side and then left with EK. I'm just going to change it around. So I'm going to have EK. I'm going to have, I like putting my stuff in brackets, 4,09 times 10 to the exponent negative 14. If any numbers go over the equation sign, the sign changes. So this becomes negative 6,63 multiplied by 10 to the negative 34. And I still have my threshold frequency, which is 4,4 times 10 to the 14. Once again, my darlings, if you're going to decide that you want to do it little by little, maybe work out the work function first, then get an answer, then take it over and so forth. Make sure that you write down the entire answer. If it gives you 14 digits after the comma, write that, because the more you round off your answer, the more incorrect it actually becomes. So I'm just going to plug it in like that. I prefer this. I make less mistakes. Trust me, I also make mistakes. 4,09 times 10 to the exponent negative 19. So for less mistakes, I prefer doing it all at once. 6.63 multiplied by 10 to the exponent negative 34. Close that bracket. 4.4 multiplied by 10 to the exponent 14. And let's see what I get there. So I get a kinetic energy of 1,17. The 2 is less than 5. It will not affect the 7. So this becomes 1,17 multiplied by 10 to the exponent negative 19. Remember, your SI unit for kinetic energy is then a capital J, which is then for joules. So we just had to find the kinetic energy of the most energetic electron that was ejected in this question. So remember, the metal had a threshold frequency of the 4.4, and that's how I got the 4.4. The energy that I used here was the transition between energy level 4 and energy level number 2. They wanted the EK. So technically, I had everything to my disposal. And as you can see, these questions are very repetitive. And if you can understand between the link between the threshold frequency and work function and energy and all that stuff, you can answer any question. And how I always teach my kids, if you're reading a question, use a highlighter, because some of you guys overread a lot of information. So as you can see how I'm underlining to remind myself and all that stuff, it's very good to do this. Okay, let's look at our next question. So here we are told another metal R remember, different metals have different work functions and threshold frequency. Has a threshold frequency of 7,5 times 10 to the 14. Just want to get this one right. This was 4,4, ne? This was 4,4. This one is 7,5. This one's very high. And that is also then in hertz. Now the question is, will the photon produced in 2.1.2 be able to eject electrons from the surface of metal R? Right? Write down yes or no and give a reason for your answer. So now remember, this one goes back to the first one that we did when we had two diagrams. We had A and B, we had potassium and cesium. Then we were told that they were using the same wavelength of UV light and the same frequency or intensity of the UV light. Then they asked us, will there be a reading in circuit number B? Right? Then we had to find out, will the UV light produce the more or less of the minimum frequency that potassium needs to eject an electron? This is something similar to that question. So we're going to go back to question 2.1.2, which is this one here. And in 2.1.2, I can see that the frequency that this electron will have is 6,17, right? We needed to calculate the frequency of the photon produced, 6,17. In this case, they're telling me that the threshold frequency is 7,15, right? So now, will it then eject? No, it won't really eject. So we need to give a reason. No, this is 7,5, that's 6,17. Remember what I said. If you're going to give a statement, give a yes or no, you get a mark for that. And then show the examiner whether you see that there's a link and so forth, and then give a reason for your answer. So between yes and no, I've chosen no, because I can see that the frequencies are definitely not the same. So let me just extend my page here. So there's various ways you could have written it. I'm not sure how many question marks was this, but it should be maybe 2 or 3. So the first one, we could have therefore said that the threshold frequency, is greater than the frequency of the electron, frequency of the photon. So let's see. I want to show you that. Remember the threshold frequency, this is the threshold frequency, this is the minimum frequency required to eject an electron. It's 7.5. But when we go to 2.12, we see that when the transition between energy level 4 and 2, this poor photon will only have 6,17. So it doesn't even reach the minimum of 7,5. So that's definitely, that's too much. The 7.5 is a lot. So no, it won't. Or you could have said, I'm just going to do this in blue. Let me just write or so that you don't think it's different steps. Or you could have said that the frequency of the photon is less than the threshold frequency. But you need to show the examiner, that you've got the two frequencies and you are identifying that this metal needs 7.5, but the photon can only have 6,17, which is very little. This is very high. So then you just have to show a relationship between the two. But it's a very easy topic. Do not fail it. Practice, practice, practice. All the best for the rest of your prelims, and I will see you next week.
up, peeps? Welcome to Moby School. We are here to make sure that you, yes, you get all the marks that you deserve on the go. We're here every Mondays to Fridays from 2 to 3 p.m. only on Mindset Learn TV. Now, this is a whole hour worth of revision just for you. And I hope that you've got your notepads and your pens ready and that you and your study group are game for today's revision session. Now, my name is Joe, and just like you, I am also in Matric, and I'm here for a whole hour to make sure that I ace my final exams. And I hope that you will be doing the exact same thing. Now, do remember that we love hearing from you guys. So log on to our Facebook page, which is